Hello and welcome. Thank you for joining me. My name is Alon Sela, and today we're going to continue talking about the Langevin stochastic differential equation. Today I want to calculate the statistical properties for the solution of the velocity at time t. We talked about the Langevin equation, and we saw that the solution, this is the Langevin equation is given by this expression, and we saw that the solution, meaning that the velocity at time t is equal to this expression, where we said that eta at time t is a Gaussian white noise with these two properties. We said that the expectation at time t is equal to 0, and the autocorrelation function, which is this expression right here, this thing we said is equal to gamma, which is a constant, times the Dirac delta function t minus t prime. Now, as I said in the last video, even though you might not understand what is a Gaussian white noise, the only thing that you need to understand for this video is you need to understand that the expectation is 0, and this quantity right here is equal to some constant times the Dirac delta function. We're going to use these properties, and we're going to use them to calculate the statistical properties. So let's start with the expectation for this for the velocity at time t. So basically we want to calculate the expectation of v at time t. So let's see. So basically we want to calculate this thing right here, the expectation of v naught times e to the minus gamma t plus 1 over m, the integral from 0 to t e to the minus gamma t minus t prime times eta at time t prime dt prime, the expectation for this expression. Now we can break the expectation to 2 because it's a linear operator, so we can actually do the expectation v naught e minus gamma t plus the expectation of 1 over m, the integral from 0 to t e to the minus gamma t minus t prime eta at time at t prime dt prime. And now note that this expression is a constant. We have some initial velocity times a constant, so this quantity, the expectation of a constant, is just the constant itself, so v naught times e to the minus gamma t plus this thing right here can go outside of the expectation because it is a constant, and now we have the expectation of this expression 0 to t e to the minus gamma t minus t prime eta at times t prime dt prime. And now the thing that we need to understand is that the only thing that is random here is this Gaussian white noise. So we can take the expectation inside the integral, and we'll get that v naught e to the minus gamma t plus 1 over m, the integral from 0 to t e to the minus gamma t minus t prime. And now we can write the expectation inside the integral, eta at time t prime dt prime. And now we are going to use this property of the Gaussian white noise, which is that the expectation at time t is equal to 0. So we have that this thing right here is equal to 0. Note that it doesn't matter the actual time. Okay, so I can put, let's if I plug here t is equal to t prime, then I'll get that the expectation for eta at time t is equal to the expectation of eta at time t prime. Okay, so this thing right here is 0, and which means that the entire integral is 0, because 0 times this expression is 0, integral of 0 is 0, and we are left with v naught e to the minus gamma t. So the first solution for this video is that we got, let's do it in green, so the expectation for the velocity is v naught e to the minus gamma t, which means that on average it doesn't matter the velocity that we are started with. Or let's put it the other way. The expectation for the velocity is the initial velocity times e to the minus gamma t. Now let's continue. Or let's make it in another video. In the next video, I'm going to explain how to calculate the variance for the velocity at time t. So I hope you joined this video. Until the next time, I'm Alon Sela. Bye bye.